Alright, so here we see a picture of a bottle of ibuprofen. Many people use ibuprofen as non-prescription pain medicine, sold over the counter, and it's used to reduce pain and synthesize ibuprofen. It shows here 3 different steps. And it says it exhibits an impressive atom economy. And so in your textbook it goes into some details about synthesis of ibuprofen. Alright, so the next learning objectives here are we're talking about quantitative chemical analysis, fundamental aspects of titration and gravimetric analysis. And last week we were able to do a titration between trying to determine the concentration of sodium hydroxide. And we used oxalic acid, which is a weak acid, and had a acid-base neutralization reaction. And you guys were able to determine the concentration of your sodium hydroxide stock solution. And we're also going to talk about gravimetric data and analysis and being able to use stoichiometry, okay, in order to use your titration and gravimetric data to figure out concentrations of solutions. That's the point of doing a titration, and gravimetric analysis to determine basically the mass of your product produced, and using stoichiometry. So here with quantitative analysis that is used to determine the amount of or concentration of a substance in a sample. Okay, so quantitative analysis is different from qualitative analysis. Quantitative analysis is always specific about the amount of concentration of a substance in a sample, whereas qualitative analysis is just determining what the substance is. Is it mercury? Is it lead? What's in the sample? So with quantitative analysis, we're going to discuss 2 different types: gravimetric analysis and titration. We've had experience with titrations from last week. We also have experience with gravimetric analysis, in a sense of weighing out our product samples, our products after experimentation. We just haven't done much of the math associated with those types of analysis, and so that's what we're going to do here. And so we need to know some vocabulary words. So we're talking about titrations. The titrant is a solution containing a known concentration of one reactant, and the analyte is a solution containing a reactant of unknown amount or concentration. So measuring the volume of the titrant solution requires, for a complete reaction with the analyte, the equivalence point of the titration allows calculation of the analyte concentration. So here they're talking about when you do titrations, when we did our experiment last week, we really only did half of an experiment, because all we did was we found the concentration of sodium hydroxide. To do like a real full titration, it requires 2 different types of titration. The first titration, you're going to figure out the concentration of sodium hydroxide, which is what you guys did. But the second time, you're going to find the concentration of an unknown, okay, using your experimentally determined concentration of sodium hydroxide that you found. And so, to add on to the experiment we did last week, since you found the concentration of your sodium hydroxide solution, then you could take like a solution of peach juice or apple juice or something, and it has acid in it, and then you could have taken your sodium hydroxide and reacted it with the acid, acid that you see in fruit juices, like citric acid, for example, and then you can figure out the amount of citric acid that was in your fruit juice. And so that's what they're talking about here when they say measuring the volume of the titrant required for a complete reaction with the analyte. The analyte in that case would have been your citric acid, your apple juice, and then calculating the concentration of citric acid in your apple juice. That's a typical example that you would see. So with titrations, you have indicators, okay, because you have to have something that tells you to stop adding your sodium hydroxide. And so last week we used phenolphthalein. And so indicators in general, and there are lots of different types depending on the reaction you're doing. You know, phenolphthalein will turn color at certain pH. There are other indicators that will turn different colors at different pHs, and so it's basically depending on what reaction you're doing in order to figuring out what indicator that you need. So anyway, you know, the indicator is going to impart a color change at or near the equivalency point of the titration. So it's going to turn a certain color when it has a certain pH value. So the volume of the titrant measured is called the endpoint. Okay, so when you reach the endpoint of the reaction, that is the point in which you stop the reaction and you measure your volume added. So the difference between the equivalency and the endpoint should be negligible. So we're assuming that they're pretty much the same thing. Here we see a picture of a burette that's being filled with a blue colored solution. And so here they're telling you, you know, with burettes you can read the measurement to the nearest 0.01 milliliters. Okay, and so you guys did that last week. And so now we need to do a calculation here, similar to what you did last week. It says the endpoint of the titration of a 50 ml sample of aqueous hydrochloric acid was reached by addition of 35.23 ml of 0.25 molar solution of sodium hydroxide titrant. The titrant reaction is, and they give this balanced chemical equation below here, hydrochloric acid reacting with sodium hydroxide yielding sodium chloride and water. What is the molarity of the hydrochloric acid? Alright, so let me switch over to doing this by hand here. So here's our balanced equation. Okay, we used 35.23 mL of a 0.250 molar solution of sodium hydroxide. They're asking for the molarity of hydrochloric acid. So that would be equal to the moles of hydrochloric acid per liter of solution. Okay, so I need to find the moles of hydrochloric acid. If we look back at the question here, it says they use 50 ml sample of aqueous HCl. Okay, so that is going to be our volume for the solution. All right, so 50 ml, so 50 mLs of HCl, and that's 0.05 liters. All right, so 5 liters of solution. Okay. So what we're having to do here is find the moles of HCl, and so we're going to have to start out with the volume of sodium hydroxide used. Okay, so we have molarity and we have volume, so we can find the moles of sodium hydroxide used that way. Alright, so I'm starting out with 0.250 moles of sodium hydroxide per liter of solution. Right? That's molarity of sodium hydroxide. And then if I multiply it by the volume here in liters, so 35.23 milliliters is 0.03523 liters. Right? If I divide it by 1,000, moving the decimal point over 3 places to the left, so 0.03523 liters. All right, so liters cancels out. I'm left with moles of sodium hydroxide. I just do the calculation, so 0.250 times 0.03523, and that is 0.00881 moles of sodium hydroxide. Alright, so now I have moles of sodium hydroxide, 0.00881 moles of sodium hydroxide. Now I need to go from moles of sodium hydroxide to moles of HCl using my molar ratio. And so here it's 1:1, so that's easy enough. So for every 1 mole of sodium hydroxide, there's 1 mole of HCl that reacts with it. So it's going to be 0.00881 moles of HCl. Alright, so that's my volume value here, 0.00881 moles of HCl. Okay, divided by the volume of the solution. I get, let's see, I get 0.1762 m, and so let's see, we're starting out with 3 there, so it's going to be 176 mole, and that's HCl. Okay, so switching gears from titrations to gravimetric analysis, and so it says type of analysis in which a sample is subjected to treatment that causes a change in the physical state of the analyte that permits separation from other components of the sample. For example, mass measurements of the sample, the isolated analyte, or some other component of the system used along with known stoichiometry of the compounds involved permit calculation of the analyte concentration. Commonly, the analyte is separated by subjecting it to a precipitation reaction. Okay, so here's a picture here where you have 2 reactants that are soluble. Both the reactants react completely, and you get a product that precipitates out. You have another product that's aqueous, and so the precipitated product you can filter. Okay, remove the liquids, dry it very carefully, and measure the mass of the precipitate, and then do some calculations. You have a theoretical calculation based off of your balanced chemical equation, and then you have your actual, which is your actual mass. You compare the two and do figure out your percent yield. So here we have an example where we're starting out with a certain mass of magnesium sulfate. It's dissolved in water. It's treated with excess barium nitrate, okay, resulting in precipitation of 0.6168 grams of barium sulfate. What is the concentration, mass percent, of magnesium sulfate in the mixture? Alright, so I'm switching over here to example 4.15. Here we have, we're figuring out the mass percent of magnesium sulfate, and so that's going to be equal to the mass of magnesium sulfate divided by the total mass of the sample times 100%. And so they gave us total mass of the sample here is 0.4550 grams. Alright, so it's going to be 0.4550 grams. But I need to find the mass of magnesium sulfate. Okay, and so they give me the mass of barium sulfate. So here, looking at my balanced chemical equation, I need to write it down here. 1 mole of magnesium sulfate reacts with 1 mole of barium nitrate to yield barium sulfate and magnesium nitrate. Alright, so we're starting out with 0.6168 grams of barium sulfate. Alright, I need to find my mass of magnesium sulfate produced in this reaction. So I need to go from mass of barium sulfate to moles of barium sulfate. So I need to find my molar mass of barium sulfate. Alright, so there's 1 atom of barium, and if I look at the average atomic mass, that is 137.33 grams. 137.33, and then for sulfur, it's 1 times 32.07, and then for oxygen, it's 4 times 16, which is 64. And then add these together to get the molar mass. I get 233.4 grams per mole. So 233.4 grams for every 1 mole, and this is barium sulfate. Alright, so units here cancel. Now I have moles of barium sulfate. I need to go from moles to mass. I'm sorry, moles to moles. So 1 mole of barium sulfate is equal to 1 mole of magnesium sulfate. This is what I'm getting to. It's the same. It's 1 to 1. But I was pointing to a different thing. But anyway, we're starting out with barium sulfate. Did that part right. It's just I was looking at the wrong guy here. So it's 1 to 1 here. So for every 1 mole of barium sulfate, it's 1 mole of magnesium sulfate. So it's 1 to 1. So the math doesn't really change anything. So, but we're going from now we've had moles of barium sulfate. Now we're going to moles of. Now we have moles of magnesium sulfate. Now we need to go from moles to mass. So one more step here. So for every 1 mole of magnesium sulfate, so many grams. Again, I'm having to figure out my molar mass for this big thing here. Alright, so 1 times the molar mass of magnesium is 24.31. For sulfur, it's 1 times, so it's 32.07. For oxygen, it's 4 times 16, and that's 4. So, this together, I get a total of 100. So a total of 120.38 grams per mole. 120.38. So 120.38 grams. Alright, so that's magnesium sulfate. Alright, so now multiplying the top parts across, like 0.6168 times 1 times 1 times 120.38. And that is 74.250 over 1 times 233.4 times 1 times 1. And so 74.250 divided by 233.4. And I get a 0.318, and that's grams of magnesium sulfate. Okay, 30.318 grams. So that needs to go right here, 0.318 grams. Okay, there. Okay, to figure out my mass percent of magnesium sulfate. So when I do the math, I get 69.89%. Looking at my numbers here, so 69.9%, and that's magnesium sulfate. Alright, so that's my mass percent. So what they were saying when they said there was a sample of, if you read the question again, that 0.4550 grams, it says it's a solid mixture containing magnesium sulfate. It's not 100% magnesium sulfate. Okay, we know the mass of barium sulfate that was produced. All right, so we can back calculate to figure out theoretical mass of magnesium sulfate that should have resulted because we knew the product of barium sulfate that we had. So we can back calculate to figure out how much magnesium sulfate we had in the for the reaction. Okay, so the mass percent is given the mass of magnesium sulfate actually theoretically calculated divided by the total mass of the sample, which is a mixture of magnesium sulfate and other things. Okay, so by mass the amount of magnesium sulfate in that sample at 0.4550 grams of sample is 69.9%. All right, so now we need to talk about combustion analysis. So it says the elemental composition of hydrocarbons and related compounds may be determined through gravimetric method known as combustion analysis. A weighted sample of the compound is heated to a high temperature under a stream of oxygen gas, resulting in its complete combustion to yield gaseous products of known identities. So, combustion analysis, the complete combustion of hydrocarbons, for example, will yield carbon dioxide and water vapor as the only products. Gaseous combustion products are swept through separate, pre-weighed collection devices containing compounds that selectively absorb each product. The mass of the absorbed products can then be used in an appropriate stoichiometric calculation to derive the moles and mass of the relevant element. So here's a picture of a case where we see a combustion reaction. Here you have an air intake allowing oxygen to go into the sample chamber, and here we have the sample in a furnace, and it's producing a lot of heat. It's a combustion reaction, so the products of this reaction are going to be carbon dioxide and water, and then you're going to have excess oxygen and some other gases too, especially if it's allowed to be open to the atmosphere. You have a water absorber such as MgClO4, and it's going to absorb some of that water. And then you can also have a CO2 absorber such as sodium hydroxide. And so all your gases are going through here, but you're absorbing your CO2 in your water, okay, which are the products of your combustion reaction. Okay, and that's how they're able to determine the mass of water and CO2 produced by the differences in the absorption before and after they're allowed to absorb water or CO2. And you're able to basically weigh the masses of your products. Alright, so here we see an example 4.16. Polyethylene is a hydrocarbon polymer used to produce food storage bags and many other flexible plastic items. The combustion analysis of a 0.00126 gram sample of polyethylene yields 0.00394 grams of CO2 and 0.00161 grams of water. So here we have an equation here. This guy over here. Alright, where we have a hydrocarbon, and you know that the subscripts here in terms of X and Y. We have excess oxygen, and we're going to yield a certain number of carbon dioxide molecules and a certain number of water molecules. Alright, so what is the empirical formula of polyethylene? So, alright, so let's think back to when we determine empirical formulas. So when we determine empirical formulas, remember we did percent to mass, and then mass to moles, and then divide by small, and then multiply till whole. Alright, so here we are not giving percentages, here we're giving mass of different things. So we're given mass of carbon dioxide, okay, which is 0.00394 grams. And then we're given the mass of water, which is 0.00161 grams of water. Alright, so that's what you're going to get whenever you do an experiment. Okay, you're going to get mass of CO2 and mass of water. So we need to go from mass of CO2 to moles of CO2, and then moles of CO2 to moles of carbon. Okay, and then for water, same idea. Mass of water to moles of water to moles of hydrogen. Okay, so that's our other part here. Alright, so let's go from mass of CO2 to moles of CO2. We need to find the molar mass of CO2. So here's CO2. It's 1 times 12, which is 12. Oxygen's 2 times 16, which is 32. So that's 44 grams per mole. Alright, so 44 grams of CO2 is equal to 1 mole of CO2. Alright, so now I have moles of CO2. I need to go from moles of CO2 to moles of carbon. So for every 1 mole of CO2, I know you haven't done this yet, but it's pretty easy. There's 1 carbon there, right? So 1 mole of carbon. Alright, so you do the math here. You take 0.00394 times 1 times 1 divided by 1 times 44 times 1, which is 44. And that is 0.000895545, and that's moles of C. Alright, so we're going to do the same process with H2O. So here we have, with H2O, it's 2 times 1, which is 2. O is 1 times 16, which is 16. It's 18 grams per mole. Alright, so 18 grams of H2O is equal to 1 mole of H2O. Alright, so their grams cancels out. We have moles of water. Now we need to go from moles of water to moles of H. So for every 1 mole of H2O, there's 2 moles of H, because there's 2 atoms of H. Okay, there. Alright, so 0.00161 times 1 times 2 divided by 1 times 1 times 18 times 1. And that is 0.0001788 moles of H. Alright, so now I have my moles of H. So percent to mass, don't need that. Mass to moles, okay, so I'm starting here. I have moles, and then my next step would be divide by the smallest number. And so that is this number here, 0.000895545. So that's 1. 0.000895545. What do I get? 0.0017888. 8954. And that gives me 1.99, which is about 2. So this is carbon and this is hydrogen. So that means that my empirical formula is going to be C1 and then H2, CH2. Okay, that's my empirical formula. Alright, so again, recapping that. I started out with 2 different masses of my products, basically, from the reaction. Okay, I converted masses of my products to moles of my products using my molar mass that I calculated there. And then I went from molar mass to moles of the compound to moles of the individual element. And I know that's new for you. It's not that hard, though, because like if you have, let me do another little side thing here. So for example, if you have, I don't know, C6H12O6 here, and you're trying to find how many, these are moles. Alright, and then you're trying to find out how many moles of carbon you have. So for every 1 mole of C6H12O6, there'd be 6 moles of C, because there are 6 atoms of C. Alright, so there's 6 atoms, so it's equivalent to 6 moles. Alright, so here, the same thing I did here. With H2O, there's 2 atoms of hydrogen, so it's 2 moles there. It's only 1 mole of carbon because there's only 1 atom there. Okay, so When we get the number of moles of each for each element, then if we look at our 4-step breakdown when we're trying to figure out empirical formula, percent to mass, mass to moles, we're starting at moles. We just calculated moles, right, for each element. And then divide by small was the next step, so that's what we did. We got 1 and we got 2. And we didn't have to multiply till whole because there were already whole numbers after we divided by small. And sometimes that happens, and sometimes when that doesn't happen, you have to, whatever number you get, you have to keep multiplying by a factor in order to get whole, until you get whole numbers. So you keep going until you get whole numbers.